All right. Good morning, everybody. I'd like to thank you all for coming along, it seems to be a lot of you, to Dev 402, Multi-Threaded Programming and .NET from the ground up. My name's Orion Edwards, and I'm a technical lead at the Gallagher Group down in Hamilton, that wonderful technological city. And I'm proud to share some of that great Hamilton awesomeness with you guys up in Auckland today. Woo. Yay! So, can I get a show of hands? Any .NET developers in here? That's good. Now, anyone worked with multi-threaded code before? Cool. Anyone found that a pleasant and enjoyable experience? There's a couple of guys out there. You guys must be really awesome programmers. From what I've seen, a lot of developers have a reasonable knowledge of the basics of what's going on with multi-threaded code. But when you get into those sort of deeper levels of what's really happening to cause those bugs, not so much. So my goal today is to try and dig into some of that, share with you a few things, and hopefully give you some knowledge that you can take back to work on Monday and apply to the code that you already have. I've got three parts to the session. First part, I'm going to show you some buggy programs. I'm going to look into them, explain and show what's causing the bugs, and give you some techniques to fix them. Second part, I'm going to use some of that and show you a basic idea of how to do some lock-free programming. The final part, sort of step up to a bit of a higher level, application level, and just give you a bit of advice about how to avoid some of these problems in the first place. So our first demo here. Let's make sure I've got the right one. Simple sample program. We've got a main thread, spins up two worker threads. Each worker thread sits in a loop and adds one to a value. See what happens. No problems, right? However, we'll run it again. And this time, we can see that in spite of the fact that both threads are just sitting there, add one, add one, add one, somehow it's going backwards. You also note it didn't fail the first time. This is fairly typical of multi-threaded code, right? Most of the time it works fine. Once in a while, blows your foot off. Let's have a look and see what's actually causing this. Now, this is sort of fairly textbook race condition, but just to illustrate, when each thread increments the value, what has to happen is you've got to go to memory. If you ever opened up a computer, you'll see the memory's over there. Underneath the big heatsink and fan, there's a CPU. So we've got to go to memory, pull the value across into the CPU. Inside the CPU, we add one. Then we've got to write it back. However, what happens? Our thread gets interrupted. Windows decides, no more time for you. I'm going to redraw the screen or do something else. Meanwhile, our other thread, dual-core processor here, runs along, cranks along for a while, doesn't get interrupted. It manages to put 201 into that memory location. Now all of a sudden, our other thread wakes up again. It's got no idea that while it's been asleep, the world has moved on. It's still got its value of 1, puts it back into memory, overwrites it. Sure enough, numbers going backwards. What can we learn from this? Well, as you can see, the operating system interrupts and interleaves the operation of threads randomly. You don't know which one's going to run first if you've got two, and they'll stop and start behind your back. This means if you're doing any sort of multi-step operations on data, it might change sort of behind your back and violate your rules. Side effects of this is that once in a while, you'll get these really bizarre problems such as addition going backwards, data corruption, crashes, all the good stuff. Well, next thing we want to know, how do we fix it? Standard, tried and true solution, use a lock. Anyone used a lock before? Excellent. So as you will know, the point of a lock is you take out a lock, make everyone else wait for you to finish so that they can't come along and pull the rug out from underneath you. Now, locks are great. Recommend using locks, but they do have some downsides. They can act as a bottleneck if you have a high-performance program, and if you have a few locks flying around in a complicated program, you can end up deadlocking your app. There are other things you can do, however, to do operations on shared data from multiple threads safely. The root of the problem is that One thing got interrupted, another thing came along during that time. What if we do it in a way that it can't be interrupted? Now, the way that modern CPUs work, or all CPUs really, there are certain things that just by virtue of how they're built, naturally are atomic. What are these things? Well, 32-bit platform, you can read or write 32 bits to memory in a single go. It's just how it works. You can't read half of a 32-bit value. Likewise, 64-bit platform, you read or write in blocks of 64. Handily, this is how big an object reference is in something like C#, also known as a pointer, to any of you guys with grey hair. There's also a few other slightly more interesting things, features of the CPU, that we can take advantage of. These things that get exposed in .NET as methods in the system.threading.interlocked class. If we look in there, we'll find these. There's increment, which does +1. Decrement, which does -1. These are really regularly used for things like reference counters. Exchange, just a bit more interesting. It lets you do a single operation swap of two values. Compare exchange, which is a swap, but it's a conditional swap. And the conditional swap is quite important, as we'll see later. There's also add, which technically you don't need, but they have it in there for convenience. So let's apply this, see if we can fix our buggy program. So before I chuck the interlocked in there, I'll just use a normal lock, and just to illustrate the difference. So we'll run that. Let it run for a while. You'll notice it's a lot slower, but it runs successfully, and there are no bugs. Now, I could run it again. We could run it all day to prove it. Trust me, it works. So how about interlocked? Well, we're doing a +1, so we'll chuck an interlock.increment in there. See what that does. Run for a while. It's quite a bit faster than a lock. And sure enough, no bugs. That's pretty cool. Another tool in your toolbox. Next demo. Going to look at our old friend, the compiler. Now, this demo, again, simple sample program. We've got two threads. Main thread, we've got a stop flag, which is shared. We set the stop flag to 0, spin up the worker thread, wait a second, set the stop flag. Meanwhile, the worker thread just sits there in a loop, waiting for that to be set. So we'll run this up, start, wait for a second, worker thread stopped. All good, right? Now, those of you with eagle eyes might have noticed that I clicked this button here to start it, and that runs with the debugger attached. Customers in release mode aren't going to have the debugger on their systems, so we'll run it without the debugger. Start up, wait for a second, still waiting. Clearly, something's not right. In order to track this down, I'm going to go and attach the debugger to the already running program. And we'll pause it. We can see this is what the main thread's doing. The main thread's sitting on this .join, waiting for that worker thread. So what's the worker thread doing? Use the threads window to jump over the worker thread, and we can see it's sitting on this line, waiting for the stop flag to be not 0. What's the stop flag? It's 1. It's been set. But we're still looping. What gives? Now, in order to show what's happening, this is where the ground up part of the talk comes in. I'm going to open the debug Windows disassembly window. Now, personally, this is not my favorite window if you're debugging stuff and you happen to land on some code that you don't have source code for. Visual Studio likes to throw this in your face. And if you don't have source code for it, for anything, it's just a big wall of assembly and you have no idea what's going on. However, If you do have source code, it's a bit more interesting. What Visual Studio will do, print out the line of C# code, followed by the actual x86 assembly code that's being executed on the processor. Now, can anyone read assembly? I'm also not raising my hand. I'm no guru at it. I know just enough to get by. So let's explain what's actually happening here. First line, move EAX, dword, PTR, ds, square brackets. Now the key here is the square brackets. Square brackets means go to memory at some location. And the location happens to be this number here. The reason for that, our stop flag is a static. Statics get stored in a fixed location. As it turns out, that's the fixed location that the compiler has chosen for my variable this time. Now move just sets it. What are we doing? We're bringing that across into the EAX register inside the CPU. If you're not familiar with the concept of registers, basically there's 4 of them that you get to use for all of your sort of actual mathematical operations inside the CPU. So we've fetched that stop flag into the CPU. We can do some logic on it. Next line, test EAX, EAX. Without going into the details of it, that's basically asking the question, is this thing 0? Next line, JNE 57. Jump, if not equal, 57. So if the thing was not 0, go to line 57. Now clearly it was, and as indicated by this little yellow arrow here. So we end up in here. Again, test EAX, ask, is this thing inside the CPU 0? If it is 0, JE, go to line 53. So hit F10 a few times. And we can see we're just bouncing around, checking this value inside the CPU. Now, you may have figured it out by now. If you haven't, here's what's happening. Main thread does the normal thing, right? Start up, sleep. The worker thread brings that flag off from memory into the CPU and just sits there in an infinite loop, asking if this value, which nobody's ever actually bothering to change, is 0. Of course it is, no one's changing it. So later on, after a second, the main thread updates the stop flag. We don't bother to reread it. We never stop, infinite loop. Now, why? Now firstly, I'm not expecting you guys to read this. It's in here if you'd like to download the slides afterwards. Why does this happen? Why would the compiler produce this kind of code? As it turns out, the compiler likes to optimize things. Makes your code faster, that's great. When it's deciding what it's allowed to do for optimizations, it's allowed to only consider the single-threaded case. If you look at that worker thread function, from a pure sort of narrow-minded view of the world, that it's the only thing happening, then logically, we read the stop flag once, we enter the loop, we don't change it, we don't call any other functions. The compiler sees that and goes, hey, this thing never changes. I'm going to save you a whole heap of time. Going to memory to read that value is expensive. I'm not going to bother. I'm just going to have an infinite loop. Off we go. Another thing which makes this tricky, though, it depends on the platform. You notice that when I ran it with the debugger attached at the start, doesn't happen. Debug build, never happen. You'll have a hard time reproducing this. Also, on the 64-bit just-in-time compiler, if you compile that for 64-bit mode, never happens. 64-bit C# compiler or just-in-time compiler simply doesn't do this optimization. However, maybe it will next time. Maybe Microsoft will introduce some more optimizations, make our code go even faster, and produce even more bugs. How do we fix it? Well, a lock will fix it. The compiler won't optimize away a lock. That would just be silly. What we can also do, though, is apply the volatile keyword. Now, the volatile keyword seems to be fairly well misunderstood. There's a lot of sort of conflicting and confusing information about it. What it does in this context is basically tell the compiler to back off. When I'm going to read the value, actually read it. That's pretty much it. Doesn't do anything else. It doesn't lock, and so on and so forth, on x86 or x64. Let's apply this, see if it works. So the thing in question is the stop flag. Chuck a volatile in there. lo and behold, after 1 second, debugger's not attached, program is fixed. Just to prove it, bring back our favorite disassembly window and have a look at the worker thread. And we can see that this code now, the same code, has produced different assembly. It's that same pattern where we've got a test, jump, test, bypass the whole loop, then we actually enter the loop. But the key point is that at each point in the loop, so the actual loop here is this, go to line 53, compare, go to line 53. Key point is, at each point in the loop, we see square brackets. We're actually going to memory and reading the value. It hasn't been optimized away. That's pretty much it. It's also proof that volatile literally doesn't do anything else. There's no locking, there's no other CPU instructions going on there. Third and final bug demo. This is my favorite one. Now, remember in our first demo, we saw that the threads sort of get started and stopped randomly, and you don't really know which one's going to run first. So, well, I'm a curious person. What does that look like? Is it 50-50 if you've got 2 threads? Is it 95%, 5%? Well, this program attempts to find that out. What we do is we have two functions, and we just fire them at the thread pool over and over and over again, and we try and work out which one runs first. The way that this is done, first thing each thread does, sets a flag. I'm done. This is my flag. Mark my territory. Move on. The next thing we do is try and read the other thread's flag. And from that, we infer, if I read his flag and he's already set it, he must have beat me to the punch. He must be running first. Remember, these flags are being accessed by multiple threads, so I've been a good programmer. I remembered to mark them as volatile. Let's see what happens. So we run, takes about that long. About sort of 77% of the time, thread A runs first. Now that's just a side effect of the fact that when I launched them, A happened to be the first in the list. About 5% of the time, thread B runs first. About a very small percent of the time, but it sometimes happens, they run together in lockstep, and I'll show you how that can happen. However, 17% of the time, something else happens. Both threads run to completion, but something else is happening. Logically, it shouldn't be possible. So, in the case where A runs first, here's what's going on. Thread A stores this flag to memory, reads the other flag. Thread B does the same. Then, when they do the calculations, they can infer that A ran first. If B runs first, it's the same situation, just slightly moved. When they run together, they both manage to write in exactly the same time. When they both read, they're both already written, so they infer that they both ran first. But logically, this still makes sense. What about that other 17% of the time? Now, as it turns out, there are 3 other scenarios that can happen. So let's say in this case, thread B runs first. The first thing it does is loads the other guy's flag. Thread A runs normally. First thing I do, set my flag, read the other one. Then thread B decides, now I'm going to set my flag after I've done the read. It does it in the wrong order. Therefore, when they do their calculations, you end up with a crazy result. So the other 2 situations, of course, is that thread A could run in the wrong order, or they could both run backwards in lockstep. What is going on here? What's happening? CPU is rearranging the reads and writes. When I first found out about this quite a few years ago now, I flipped out. I was like, you're telling me my perfectly crafted code, do this, it's just randomly doing it in the wrong order. Yes, it is. My next thought was, if this is happening, and clearly it is, why doesn't all my code break all the time? The reason for that is that CPUs which do this are very clever, and all of the sort of reordering tricks that they do they keep track of, and fix everything up afterwards. So from the point of view of your program, it all appears to be sane and fine, and you never know. Carry on. The problem comes in when you have multiple CPUs. Each CPU keeps track of its own internal shenanigans, doesn't tell the other one what's going on. How do we fix this? Well, a lock will fix it. Interlock things will fix it in some situations. What you really need is a thing called a memory barrier. Now, what a memory barrier, you can't turn off reordering at the hardware level. There's no BIOS flag, there's no Windows setting to say turn off reordering, as much as we might like one. If there was, you wouldn't enable it because it would have a severe performance impact. What we can do is put something in your code called a memory barrier. Memory barrier acts like a sort of a line in the sand or a fence. So when the CPU is moving things around, it can't move them past this fence. The way you would use one of those in .NET is with the thread.memoryBarrier function. The standard .NET lock is actually inserting memory barriers behind the scenes. That's kind of how it works. And those interlocked operations on x86 and x64, they also act as barriers because it's not allowed to reorder through them. It's just what the rules are. Let's apply this, see if it actually works. So, we can't prove it, but my theory is that this line here is being moved down. So, I want to insert a memory barrier here. If we run that, then it's a lot better, but there's still some WTFs. Why is that? Well, remember both threads can get reordered, so we need a memory barrier on the other one. Sure enough, the problem is gone. So we've proved the theory, yes, it was being reordered, and we've managed to stop it. Now, okay, we know that there's various things that are atomic. We know that reordering happens. What are the rules behind what reordering happens and that kind of thing? The set of rules that defines that is called a memory model. Each CPU and also platform, the .NET has one, Java has one, they define their memory model, and that defines what can happen. On x86 and x64, we're actually quite lucky. There's not a lot of reordering that can happen. There's only this one thing where a store can move below a load. However, on ARM, this is maybe pertinent to any of you who are considering developing for Windows RT on those nice new dual-core ARM processors. There's a whole stack more reordering that can happen. So on ARM, you will certainly need more memory barriers and things like that because it's going to do more moving of code around. To compensate for this, the volatile keyword on an ARM processor actually does more stuff. If you get into the details, it goes and explains it all, and there's a good article in the MSDN magazine 2012 which really gets into it. But effectively, it says, make it behave like x86. So you can still have some reordering, but it does turn off most of it. And it does this by inserting extra barriers. So, into part one. We've got operating system is going to break your code by running your threads randomly. Fix it with locks, and you may also be able to use atomic operations. Compiler is also going to break your code by optimizing it. Fix it with locks. Atomic operations will fix it as well. The compiler will back off when it sees these things, and volatile as well. And finally, even if we write our code perfectly, CPU is going to run it in the wrong order. So fix it with locks, atomics, or at the lowest level, a memory barrier. All right, so let's build something with these things. I'm going to show you the basic idea behind some simple lock-free programming. Now, what I'm going to show you, I'm not sure if there's an official sort of book patent name for it, but it's effectively a loop on the interlock compare exchange function. Now, remember before I said the interlock compare exchange function does a swap, but it's a conditional swap, and it will also return the old value that it swapped out. So you can build on top of that. Now, the way you do this is firstly, the thing that you're working with has to be immutable. So if you've got a list or a queue or a dictionary or what have you, the actual data structure must be immutable. Now, what this gives you is the ability for multiple threads to all read concurrently without having any problems. This is one of the main things that are touted as a big benefit of functional programming style things. Now, of course, that's great, but if we're going to have a list, at some point we want to put something in it. So we can't just have a flat, immutable list. In that case, what you do is this. Get a reference to the current one. Use that reference to build a new list. So you might copy the data, you might patch it, you might do all sorts of things. Effectively, you build a new list, and you swap it in. And you use the interlocked compare exchange function to do that swap in a single, uninterruptible step. Now, the compare part's important, because building the new value might take some time. During that time, someone else might have come along and pulled the rug out from underneath us, and our new value won't be valid. So the point of the compare exchange is to detect that and fail. If the swap fails, we go again, back to the start, reread it, rebuild the new value. Eventually, we'll succeed. This is how probably the vast majority of lock-free code that I've seen works. If you've ever used an event in .NET, such as button.click plus equals so on, if you disassemble that in something like Reflector, you don't need to go all the way to the x86 level, you'll see that's exactly what's happening. It's a loop, it's an immutable list of functions, and it's building a new list and swapping it in with interlock compare exchange. This also has some nice side effects. If you do structure your data like this, swapping in and out immutable lists, you can keep the old ones around. And all of a sudden, it becomes really easy to do things like undo. This is how the Visual Studio Text Editor works. It doesn't use interlocked because it's not multi-threaded, but it does use these immutable structures and just swapping them in and out. So when you undo, we just put the old one back again. Simple. Here is the code for it, or one variation on it. So we have some variables to store the current value in the replacement one, calculate the new one, and swap it in. These slides will all be available on the Microsoft site afterwards, of course, if you want to get the code. I also have a couple of blog entries where I go into more detail about some of these demos if you're interested in why I've done the things that I've done. And there's also the key part at the bottom, the test. We say, is it still safe to swap our new value in, or has someone else come along while we weren't looking? Now, what I'm going to do, use this to build a spin lock. Anyone know what a spin lock is? Few people. Well, a spin lock is just a normal lock, except that if one guy's got the lock, another one wants to acquire it, rather than getting the thread put to sleep, it just sits there in an infinite loop, retrying as fast as it possibly can to acquire the lock. Now, why would you want to do this? Well, it's a very simple lock, so it serves as a good building point for understanding other locks. And also, sometimes you may actually want to burn that CPU, because then you're guaranteed to get the lock as fast as you possibly can as soon as it's available. So, this sample program we have here, it's the same program as demo 1. We've got 2 threads plus running a variable together. The only difference is that we acquire my lock, and we release it around each access to incrementing the value. So, run it, and it fails because I actually need some code for the lock. So how do we code this, right? Conceptually speaking, a lock is actually really simple. It's just a flag. Has someone got the lock or not? If someone's got the lock, we have to wait. If not, we get it. So let's model that by just having a flag. And we're going to use an int, and we're going to set it to 0 if no one's got the lock. Okay, to acquire the lock, I'm going to use that interlock compare exchange loop pattern. My handy code snippet for it, so I don't type it wrong. So the thing we're dealing with is an int. Step 1, read the current value. So read the flag. Step 2, calculate the new value. Now in this case, it's pretty simple. We don't actually need to do any calculation. We're just trying to set the flag to 1. There we go. And the third part, what's our success condition? We want the swap to succeed if what? So in this case, we want the swap to succeed if the flag is 0. There we go. How about releasing the lock? Well, in order to release the lock, we first must have it. Therefore, we know it must be 1. So to release the lock, we just set it to 0. See if this works. Lo and behold, it works. That's how simple a lock can be. Let's compare this to the real actual lock that you use all the time when you're coding. What you get when you type lock in C# is a call to system.threading.monitor class, and it calls .enter and exit on it. What that does, the way I found this out, and you can find this out too yourself if you're really interested, Microsoft have a thing called the shared source CLI. They released this as part of their efforts to make C# a sort of ECMA standard way back when, in 2005, I believe it was. And what it is basically the core source code for all of the C and C++ parts of the garbage collector, the just-in-time compiler, all that stuff that you never see. And the lock's in there. Now, from that source code, you can see the first thing it does is interlock compare exchanger flag, just like our basic lock, followed by a spin, just like our basic lock. However, rather than spinning forever and burning CPU, it gives up after 10 times. Then, at this point, it falls back to an auto reset event. Now, you may or may not be familiar with these, but basically it's just a signal. That's it. When you wait for it, Windows kernel puts your thread to sleep. When someone signals it, Windows kernel will wake your thread up. To release the lock, it's another interlock compare exchange. My spin lock just set the flag to 0. They use a compare exchange. The reason for that is because the standard .NET lock supports recursion. You can have sub-functions that all repeatedly acquire the lock, so therefore they need to keep a reference count, and they do that with the compare exchange. And then if there were any threads that were put to sleep, it will be keeping track of them, and it will wake them up by signaling this auto reset event. What we can sort of infer from this is that standard lock performance is actually really good. If the lock is not contended, if no one else has got it, it's a single interlock compare exchange operation to acquire the lock, and a single to release it. That's all you get. So you're going to have a pretty hard time beating the standard lock in that case. Let's build something slightly more interesting. How about an actual thing that holds some data, not just a flag? A lock-free queue. Now this program, this is what you might call a unit test type program for a queue. There's a producer thread, and it just sits there and fires values into this queue. And there's a consumer thread, and it runs concurrently, and it sits there and pulls values off the queue as fast as it possibly can. And at the moment, it's compiled to use the standard .NET queue, which makes no claims of thread safety. If we run it, we see a whole stack of errors. Why is that? Well, inside the standard .NET queue, there's a whole bunch of data structures involving buffers and copying around and so on and so forth. It doesn't do any locking, and it doesn't try to be thread safe, so it's getting bitten by one of those 3 previous bugs. Probably just the interleaving one. That's the most common one. So let's change this to be a lock-free queue. And we need to code that up. So a queue is a bit more complicated than a lock. We need some place to store the things that are in the queue. I'm just going to use a simple array. I'm going to call it buffer, and it's going to start with nothing in it. Now, in order to add something to the queue, I'm going to use that pattern again, compare exchange loop. So first, we get a reference to the current value. We use that reference to calculate a new value. Now, this one we actually have to do some work. We have to copy the buffer and add the new item into the copy, and then swap in the copy. Using my nice function I prepared earlier, copy buffer and add item to the end, pass in the current reference, and the new item. Now, the third part, our success condition. We want this to succeed if the current value is still the current value. So that's it there. We need to implement count. So we just return buffer.length. Now, because that buffer itself isn't actually ever changing, it's safe for anybody to read it as much as they like. And finally, the DQ, take one off the bottom. So apply that same pattern. Get a reference to the value. Calculate the new value, this time by copying and removing. Remember, I've got to put the current reference in there, not the buffer. If we read it twice, then we have a window where it could change in between that. We only want to read it once. And we stash that in our return value so we can return it. Let's see if this works. Yep, runs successfully, runs to the end, no locks in sight, and yet it's thread safe. Personally, I think that's pretty cool. But, okay, so a bit of advice about lock-free programming. Guaranteed to have no deadlocks. That can be a huge win. But there's some pretty severe penalties that you have to pay for that. Firstly, it requires different data structures. We saw with the lock-free queue, we couldn't just use the normal .NET queue. We had to rebuild it from scratch. Additionally, to satisfy that requirement that the actual thing is read-only, you may have to do a lot more work. Now, if our buffer only contained at any point a couple of things. It's quite fast to copy it around all over the place. If our buffer contained 5,000 items and we had to copy it over and over again, that would be a huge performance problem. Now, there are things that you can do to mitigate this. You can split it up into sub-buffers and you can join them all together and you can build all these fancy data structures. People who write code in F# and Haskell do this all day long and they love it. It's a heck of a lot of work. Now this, for me, is the kicker. If you're going to go into the realms of lock-free programming, you have to, as soon as you get off the happy path of just normal locks, normal locks are great because the Microsoft guys who wrote the locks have considered all of the things that can go wrong. If you just lock and unlock, you're good. As soon as you stray off that path, you have to consider that. You have to know the memory model. Each time you write any code that might be accessed by, any data that might be accessed by multiple threads, you have to think about, is there a situation where our thread could get interrupted that might break our code? Is there a situation where the compiler might optimize this away? Maybe it's going to rip something out of a loop and move it up. Could that happen? And the real one is, could this thing be reordered? So you have to know, am I going to run in x86? If I am, do I need some memory barriers? Am I good with just my interlocks, whatever? Am I going to run on ARM? I need a whole stack more memory barriers on ARM. All that stuff, that's a lot of mental load, and it's really easy to get wrong. Also, you can certainly get performance benefits out of this, but as I mentioned, because of those data structure requirements, you may have to work pretty hard. End result, you're almost always better off using locks, but certainly knowledge of how this stuff works means that in the off chance where you're not, the 1 out of 100 situation where this might work, you can do it. Also, just knowing how this stuff works, personally, I believe, helps a lot in just designing normal programs. You can help write better code even if you never use it. Final part. Seen, there's a lot of stuff that can go wrong to break your code at the low levels of multi-threading. So for me, the best way to avoid these kinds of bugs is to avoid that kind of code entirely. The main thing that I want to share with you, talk about to help with that, is having a threading model for your application. And also, I'd just like to share a few sort of tips at the sort of code level that I find have been really useful. So what's a threading model? Threading model is pretty simple. It's the set of rules for your application or applications or whatever they are that define what threads there are, can we create more threads, how do those threads interact? And particularly important here is what threads are allowed to access what data. If you limit some data to some threads, like if you say this bunch of data can only be accessed on this single thread, then it means that you automatically rule out all of those multi-threading issues by ruling out the threads. So you can get a lot of benefits out of that. Key point I want to make is define this early on. If you're in a team environment, you always have that situation where 3 guys are doing the right thing and one guy doesn't quite really know what the other ones are doing and he goes off into the woods and breaks everything. This is even worse with multi-threading. You need to get everyone on your teams to know what the threading model is and stick to it. Some examples of threading models. Firstly is the free-for-all model, otherwise known as no kind of threading model at all. This is what you get when you don't define something. You just have all your core data structures floating around, bunch of random threads, reading and writing, and obviously the downside of this is that as soon as one of those guys screws up, you forget to put a lock in, or you put a lock in the wrong order, bang, game over. The other extreme is single thread. You've only got one thread, you can't have threading bugs. Awesome. This is how JavaScript works, basically. You only get one thread. And you can make that thread do things useful, do useful things by feeding it events from an external source. The vast majority of UI applications are kind of structured like this. WPF, WinRT, JavaScript. They've all got this one core thread that owns all the data, and it just gets events fired at it. Downside, of course, is that if you've only got one thread, that thread might be busy, looks like your application is hung. So you can extend that. If you keep this next threading model, keep it so that all your core data structures are still owned by the main thread. You have to be on the main thread to get them, but if you want to do some computationally expensive work, or maybe like a long network sort of operation and you're not using async, you can ship that off to a worker thread. When the worker thread's finished, ship the results back. This is great. You get to use, take advantage of multiple CPU cores for high performance. But you do need some discipline. It's awfully tempting, and I've done this a couple times just by accident. In one of your sort of worker functions, oh yeah, I'll just go and read that core data structure. I'll just do it. Surely it'll be fine. As soon as you do that, again, game over. Third threading model example. Again, you can there's no such thing as the right threading model. These are just examples. Is where you partition up your data. So rather than just having all the core data being owned by the one thread, you can say this thread owns this bunch of data. This thread owns this bunch of data, and so on. If one guy wants to get some other data, post a message off to him to say, please send me this data back, and he'll send you a copy back. Now that's kind of good. If you divide all your components up, it makes it easier to scale. If you've ever heard of the programming language Erlang or the term actor-based concurrency, this is it. By the fact that you're saying no data, all the data is only accessed by the thread that owns it, again, you're avoiding these issues. But you trade them off for this whole request response all day long kind of thing, and it can be quite annoying to work with. One thing that worked really well for us at Gallagher, we had a really complicated big UI sort of application, and it was a WPF application. So we followed the WPF threading model, where you've got the one UI thread, it owns all of the data. Now, we wanted to do some more expensive, the odd sort of computationally expensive thing, so we fired random things off at the thread pool to do some work. Later on, we ended up having this sort of bottleneck where we had lots of events coming in, and there was a lot of expensive processing that had to happen. And we didn't want it on the UI thread, but it couldn't be on the random background thread pool threads because there's like 10 of them and they all run concurrently. And so what we did was we kind of mixed and matched. We've got the one dedicated thread pool thread, and we've got this one second dedicated events processing thread. And then the other sort of random thread pool threads for ad hoc use. That works really well for us. So you can sort of mix and match all these models together to give you a lot of benefits. There's no such thing as the right model, as long as you have one. That's the key point. A few quick tips. The root cause of all threading bugs, as we've seen, is modifying shared data. Functional programming guys will tell you, never have shared data. You can't have it. But this is the real world, we have to. In saying that, if you can avoid it where possible, or make it read-only and immutable where possible, then you start cutting out large classes of errors. And if you can sort of isolate your shared data down as small as you can, then you end up in the situation where you only have to worry about those threading issues for that core stuff. The rest of it, where it's read-only or where it's not shared, no problem. I didn't demo any deadlocks in this thing. If you're at my session last year, at last year's TechEd, anyone? Not very many of you. Well, if you were, you'll know about memory dumps. Not a lot of you weren't. So what a memory dump does is you basically snapshot all the memory of the program, dump it to a file. You take that file off your production system or your client PC, bring it into Visual Studio, load it up, call stacks, all there. Usually these are actually really easy to solve. You just bring up the memory dump. Oh, look, this thread's holding this lock, this thread's holding this lock. They shouldn't be doing that, let's fix it. Otherwise, I'd love to say there's some new fancy tools that will help you diagnose these other kind of race conditions. To my knowledge, there isn't. The best thing I know of is actually code inspection. Just use your logging and things like that to say, okay, we think it might be in this area, and then you just have to simply kind of read through the code. Apply those rules that we saw before. We know, could we be getting interrupted? Could we be getting reordered? Could this happen to this code? No, carry on. This is a thing that I've seen lots. If you use a framework like WPF or WinRT, anything with data binding really, you end up in a situation where you've got a bunch of data objects and you might data bind to them. And so for the data binding, they need to fire a change notification. My name field has changed, please update the UI. What I've seen a lot of, and this has happened probably at least a dozen times in the last year, big sort of deadlock, crash the server type things, someone's holding a lock and firing a change notification. As soon as you fire a change notification, you're executing some random code that someone else wrote maybe 5 years later, and they might be acquiring a lock, and you end up in a deadlock, basically. Number one cause of deadlocks I've seen. Simple fix, fire the change notification after you release the lock. Other things which, personally, I find this to be really great. Attributes in .NET, you can just make them up. You can make your own arbitrary attributes. They don't do anything. You can just use them to tag bits of code. Personally, I like to make attributes that tag what thread code should be run on, like UI thread only, or if it's thread safe, you can tag it as being thread safe. The number one reason for this is to make that threading model visible. If someone's code reviewing your code to try and find a bug, if they can see this thing is not thread safe, yet it's doing some threading, immediately it's a red flag. If you can't see the threading model from within the code, you're going to miss that. As I mentioned before, these attributes don't do anything. They could also just be comments. From my experience, developers give a lot more respect to these, even for some reason, than they do to comments. So I'd recommend that. You can also go one better. If you're on the wrong thread, actually do a check, throw an exception, crash the program immediately. If you don't crash the program immediately, you're going to end up with some silent data corruption, which is going to crash the program later, which is always worse. If you'd like to learn more, a few sort of links. This first one, this is the article I read years and years and years ago where I first learned about memory barriers. It's really well written. It's quite good. I'd recommend it. Secondly, a link to Joseph Albahari's C# in a Nutshell book, which is online, the threading chapter. It goes over all this stuff and it's really well written. Finally, Joe Duffy, who's a core Microsoft guy, builds the .NET parallel extensions and things like that. He's got a whole stack of stuff on his blog. And if you're interested in any of the core reasons about why .NET does things like the way it does and the internal logic that went into it, their thoughts about how they built things, he's got a lot of insight on there. If you'd like to contact me, Twitter, Borland, that's me. You can send me an email, ask me any questions or anything on orion.edwards@gmail.com. And I also have a blog. Now, I'm not a prolific blogger, but I have put a couple of articles up already going over those first demos, going into detail about why I did the things I did, and going into a bit more depth about what's happening. And I will be putting more posts up for these other things. Please evaluate the session if you enjoyed it, and thank you all for coming.